Hi there, Chemistry 11. So today we're going to continue our examination of stoichiometry, and we're going to expand it into looking at solutions. So before we start that, I want to kind of just revisit stoichiometry because I think it intimidates a lot of people, but I also think it's really important that the learning be there because it's an important part of Chemistry 11. So I guess what I want to do is talk a little bit about the moles bridge. So here's how I see it. The moles bridge is all about unit conversion. In fact, stoichiometry is all about unit conversion. With the moles bridge, what you have is a multi-part situation that is the same set of steps. You're doing the same kinds of things for any stoichiometry problem. So you're going to be given a balanced chemical equation. You will be given an amount, usually a mass or a gas volume or a number of particles, for example, of one substance. And you'll be told what the substance is, so you'll be able to figure out its molar mass. You might need that. And you'll be asked, okay, now tell me what amount of this do you need to react with it, or how much of this product will get made when you react this much of this reactant. This is the kind of information you're going to get. You'll have an input and a desired output. The point of the whole moles bridge concept is that in the middle of it all has to be the mole. You will start with a certain unit, for example, mass. You might get a mass of a substance, like I put substance 1, so M1, and you'll be given that mass. You will then be needing to convert to moles, because converting to moles is your first step. How do you do that? Unit 5 would tell you that. Mass divided by molar mass gives you the number of moles. And I put that as N1 because N is chemical amount, N1 means substance 1. Then, here's where you do your conversion. While we're on the moles bridge, some people call it the conversion bridge. It doesn't matter, you're doing the same thing. You're taking your moles of the one substance and you're multiplying it by the molar ratio in the balanced chemical equation. So you will take your N1 and you're multiplying it by, look what I wrote here, N2 over N1. That's a fraction. In fact, it's a unitless fraction in the sense that it's moles divided by moles, except it's moles of, well, it's not entirely unitless because it's moles of one thing divided by moles of another. So what's going to cancel out here is not the mole unit, but moles of what you're counting. Here's the way that would play out. Number of moles of substance 1 times the number of moles of substance 2 divided by moles of substance 1. And you get these here, you get this fraction, this ratio, from the balanced chemical equation. So it's going to be a fraction, or sometimes it'll simplify to a whole number, and that'll give you your moles of substance 2. So it's this right here where we're crossing that moles bridge. Now, once we get the number of moles of substance 2, the one we were trying to solve for, then we can do another conversion that might be asked for. You might want volume of a gas at STP, number of particles that were being made or needed, or you might be calculating the mass that you make or you need, or you can calculate other things relating to solutions like we're going to look at today. All stoichiometry problems use a variation of the moles bridge. Information given, balanced chemical equation. Convert a known substance to moles. Do a mole unit conversion, like using a molar ratio in the balanced chemical equation. Find the moles of the other thing, and then do another conversion. Once you, I think, see that, and you see that they're really all the same problem, I think it becomes easier. We're looking today at solutions, specifically at liquid solutions, and they all happen to be aqueous, meaning in water, because in chemistry, well, water is it's a very good solvent, and so that's why people talk so much about aqueous solutions. Here's where we are at so far with solutions. Okay? You can pause the video if you want to and write that down. Those are 3 equations that you have. We have the units are of interest for examining solutions in a quantitative way for you guys. is C for concentration, and that's measured in moles per liter. N, which is your chemical amount, and that's measured in moles. And V is your volume. The SI unit for that is liters. We have three equations, which are all different ways of saying the same thing. 1, C equals N over V. Concentration equals number of moles divided by liters. One that's particularly useful if you want to convert to moles, use this one in the middle that I locked off in red. N equals CD. Number of moles equals the concentration times the volume. Because you're often going to want moles, that one in the middle is particularly useful. Also on the right here, we see V equals N over C. Volume equals moles divided by concentrations. Three different ways of saying the same equation. And what I've got for you that I'm uploading today is a worksheet on this topic. And I've chosen 3 problems from the worksheet. I specifically chose them because each of them solves for a different variable. They will all, however, work the same way. Here is a balanced chemical equation for you. This is the equation for the reaction that happens in Drano. If you take Drano, you might notice some versions of it have little bits of aluminum. You can tell it's a metal. And when you combine it with water, you get a very powerful reaction, releases gas, releases a lot of heat, and clears the drains. Here's the reaction as a balanced chemical equation. 2 aluminum plus 2 sodium hydroxide plus 2 water, so it has to happen in water, reacts to create 2 sodium aluminate, which is a weird chemical because it's an ionic compound, but it's got 2 different metals in one ionic compound. That's the way it is. Plus 3 hydrogen gas. So all the coefficients were 2 except for hydrogen, which has a coefficient of 3. Now, here's what we're told. We're told that someone wants 50 liters of hydrogen gas, which is an awful lot of hydrogen gas. But that's what they want, and they have an excess of aluminum, and they want to know how much of the sodium hydroxide solution they need to make that happen. So, the first thing I wanted to tell you is what excess is. When people say excess, they mean extra. It's just a way of saying an extra amount. There's more of this than is needed to react with all of this. Sometimes people will want to do reactions in perfect stoichiometric ratios to add just the right amount of reactant 1 to react with all of what's reactant 2, and then everything that's left over is products. But in the case of this reaction here, you might not want to do that. Aluminum foil is perfectly safe to handle, but you don't want to put your hand in a solution of sodium hydroxide. It will eat away at your skin. And so when excess is added, a bit of extra aluminum is added, more than is needed to react with all the sodium hydroxide. So all the sodium hydroxide will get eaten up. If you mix it properly, you won't have any sodium hydroxide left over and a little bit of aluminum. There's a lesson coming up on this concept of limiting and excess reagents, but that's lesson 4. For today, here's where we're at. We have a volume that's desired of hydrogen gas. And we also have this thing called the molar volume. It tells us that at STP, any gas, any mole of any gas occupies 22.4 liters. If you heat up the gas, it's going to occupy more space, and so on, so on. You can change the conditions and change the molar volume, but at STP, it's 22.4 liters per mole. So if we want to know the number of moles, we go 50 liters divided by 22.4 liters per mole gives us 2.23 moles. That's 2.23 moles of hydrogen gas that we want to make. How many moles of sodium hydroxide do we need to make that happen? Here's where we're crossing the moles bridge. We put our foot on the moles bridge because we know how many moles of hydrogen we want. To calculate the number of moles of sodium hydroxide, we say that the number of moles of sodium hydroxide, I put NaOH, equals the number of moles of hydrogen multiplied by moles of sodium hydroxide per mole of hydrogen. Well, this is a simple fraction. It's 2/3. There's 2 sodium hydroxide moles per 3 moles of hydrogen. interesting, really, because what's actually canceling out here is not, well, the unit that we're losing is not the mole unit. The answer is going to have moles, but it's moles of what? We're going to go from moles of hydrogen, the hydrogen part cancels out, to moles of sodium hydroxide. This is why it's often a really good idea to keep everything inside your equations as you go along, including all of your units, and that way you can spot whether you're on the right track or not. Here's what I get when I did this. 2.23 moles times 2 NaOH per 3H2 gives us 1.49 moles of sodium hydroxide. That's the chemical amount that we need, but they didn't ask for that. They asked for the volume, and they gave the concentration. So to make that happen, well, we calculate the volume of sodium hydroxide being V equals N over C. Just like I said, that might be useful sometimes. 1.49 moles is our molar amount, divided by the concentration, the molarity, 3 moles. And I get 0.496 liters. So that's the answer to question 1. The other question I'm going to review is question 6, A and B. And again, this is just because we're solving for 3 different variables in the 3 questions. 2, 3, 4, and 5, I'm going to leave those to you guys. All right, I'm going to move over here. So for this question here, my apologies. Question 6. The iron present in a sample of iron ore is converted to Fe2 plus and titrated with dichromate ion. All right, there's a fair bit to unpack right there. First of all, the dichromate ion is one you might not have heard of. It's a very big ion with 2 chromium atoms and actually 7 oxygen atoms in it. It's a polyatomic ion, and actually it's negative. It's used as an indicator ion. The reason for that is that solutions of the dichromate ion are very brightly colored. I think that they're red. I can't remember for certain. They have a very bright, vibrant color. So when dichromate is present in solution, you can tell when it's all been used up in the solution. The color changes back to whatever boring color there was before. So for this reason, dichromate is used in a lot of what are called titrations. A titration is described in your notes package as well. It's a procedure that is used to figure out what the concentration is of something in a solution. So typically with a titration, you're combining one reactant with another reactant, and there will be a color change when the reaction is complete. And if you stop exactly when you get that color change, you can use this kind of math to figure out what an unknown concentration was of one of your substances. If you know, we'll maybe get into that a little bit later, but if you have the other things that are known within that equation, you can calculate an unknown concentration using titration. So here we've got a situation where someone wants to figure out how much iron there is in a solution. Maybe they're thinking about building a mine at a certain place, and they want to know if there's enough iron mineral that it's in the rock that justifies opening a mine, if there's enough of a concentration. So specifically here, they're titrating the Fe2 plus to figure out what the concentration is of Fe2 plus in there. To do that, you have a balanced chemical equation, the dichromate ion plus 6 iron 2 plus 14 H plus. This is happening in a strong acid, becomes 2 chromium ions, Cr3 plus, 6 iron 3 plus ions, and 7 water. That's a big balanced equation. and we have to work with it to calculate two unknowns. One is we're being told we have 17.6 milliliters of a 0.125 molar dichromate ion solution is needed to titrate, that is to say, react completely with a 25 milliliter sample of Fe2 plus solution. So the point where the reaction is complete but no more has been added is called the end point for the reaction, and that tells you when your reactions are completely balanced. What's the molarity of the Fe2 plus? Here's how we get there. For when you're entering that moles bridge, you need to be calculating chemical amount. You have something that you have enough information already to calculate chemical amount based on your chapter 5 equations. In this case, we're calculating the chemical amount of the dichromate ion. And we use that formula again, N equals CV. It works for an aqueous solution or any solution. N, molar amount, equals 0.125 molar multiplied by your 0.0176 liter solution. 0.0176, that's the same thing as 17.6 milliliters. So what we get from that is here 0.022 moles of the dichromate ion. See, I'm writing a little bit of extra stuff up there to make sure I don't lose track of what I'm counting. So the next thing we do, having done that that starting mole chemical amount calculation, is we need to multiply by a molar ratio. You always multiply by a molar ratio. So in this case, we say, all right, how many moles of Fe2 plus? Well, we're going to get that by saying moles of Fe2 plus equals the moles of dichromate. I put Nd for moles of dichromate, times moles of Fe plus per mole of dichromate. That's the molar ratio. What is the value for the molar ratio? Well, we can get it pretty easily. It's going to be, we have 6 Fe2 plus for every 1 dichromate ion. 6-to-1 ratio. We're multiplying by 6. 6 Fe2 plus per 1 dichromate. When you do that, you end up finding this value over here. Let me see if, no, it's not visible. I'll tell you what it says. 0.0132 moles of Fe2 plus. That's what you see right there. So the next thing to do is going to be to calculate that concentration. And that's not going to be hard because you've got the molar amount, 0.0132 moles of Fe2 plus, and we're told the volume we're working with, 25 milliliters. You want to be sure you get your unit conversion right there. It's not 25 liters, it's 25 milliliters. And the concentration ends up being calculated as C equals 0.0132 moles over 0.025 liters is 0.528 molar. 3 sig figs, by the way. Having that figure, we're now going to be able to do part B actually pretty quickly because, well, we want, if we were starting at the beginning, we would say, oh, what are the moles of dichromate? And we would get there and get that 0.022. All right, then we get this again, 0.0132, but we already knew that from part A. All we really need to do that's new for this one is to calculate the mass. Well, mass equals moles times molar mass. That's a chapter 5 equation for you. So in that case, molar mass of iron, 55.8 grams per mole. The mass equals, mass times molar mass equals the number of moles of iron 2 plus times 55.8 grams per mole, because 2 plus and 3 plus is all 55.8 grams per mole, equals 0.0132 moles times 55.8 grams per mole. Anyways, after all that rigmarole, we get 0.737 grams. Or you could say, as a full answer, 0.737 grams of Fe2 plus. Plus, I guess there would be some extra mass for whatever negative ion it was paired with. So, I hope that helps. I know stoichiometry is not easy. I'll probably be coming back to this with doing some kind of like summary chapter assignment that, where you're expanding your ability in this a little bit or just working on it a little bit. Because again, it brings together the learning from elsewhere in Chem 11 in a way that's really important for anyone who's going on to take any kind of further training in chemistry. So that's why I'm putting so much emphasis on it. Anyways, I hope you find that useful, and I will hear from you soon. Bye for now. Have a great weekend.